recording. Today is the 23rd. Okay. It's 2:23. We said really early on in this chapter, what's a chemical reaction? You said, some of you said, you mix two chemicals together and they go, spark or boom or fizz or whoosh. But then I said, well, do any two chemicals mixed together do that? And you pretty much universally said, well, no. There are lots of things that can mix together and there will be no reaction. What an activity series does is it allows you to predict that. So rather than just mixing it all together and figuring out if something happens or not, which is not a safe way to proceed, an activity series is a list. It's a series. And you can look at this and say, oh, this thing is more reactive than this thing. This will react with that. It will not react with that. It's just a list. List of elements organized according to the ease with which they undergo certain reactions. So we're going to take a look at a real live activity series. Okay. The next one doesn't say much, but it would have told me the page number. 266. What we can do with an activity series is we can look at two things and say, will this reaction run or not? And you're going to have a whole sheet of practice for that today. As you look at that list, activity decreases down the list. Okay? So the most reactive things on the list are at the top. As you go down, the activity decreases. The other important point, if you look at that chart in your book, notice that there are actually two different columns. One column is your metals, the other is halogens. Remember when we talked about replacement reactions, so for instance, NH4Cl plus Br2, what can the bromine replace? The ammonia or the chlorine? How many of you would say ammonia? How many of you would say bromine? How many of you are not awake enough to, or chlorine? How many of you would say chlorine? Sorry, how many of me are not awake enough yet to make questions? Okay, right, bromine's a halogen, chlorine's a halogen. If any replacement's going to occur, it would be those two. The activity series for halogens is separate than the one for metals. So it's apples and oranges. You can only compare halogens to other halogens. You can only compare metals to other metals. Capiche? Yeah? Wunderbar. Okay. We have, this would be copper 2 chloride and zinc. Yeah? So if a single replacement reaction was going to occur, what could the zinc possibly replace? The copper or the chloride? The copper. Metal to metal. So now what we need to look at, these are the two that we're comparing, is on that activity series, which of these things is more active? So look at that first column. I could actually take a picture of this, huh? Okay. Where is zinc compared to copper? Higher or lower? Higher. Which means zinc is more active than copper. The higher up it is on the list, the more active it is. So, will zinc replace copper? Yeah. So what we'll get out of this is ZnCl2 and Cu. The metaphor for this goes back to our dance metaphor for reactions. So, say you have two choices of dates. Okay? And the date you're currently with, copper in this case, boy, honestly, copper's kind of a slug. Copper's idea of an interesting evening, sitting on the couch every single night, never leaving the house. Do you want to go do something? No. Do you want to go visit people? No. You want to go see a movie? No. You want to just go outside and look at things? No. Copper does not sound like a fun date. Zinc, on the other hand, shows up and goes, hey, do you want to go do stuff? Let's go do stuff. Let's go for a hike. Or we could go see a movie. Hey, we could go to Rogers and walk around. Oh, we could go to the park. We could go visit people. Hey, let's go see some music. Let's go do things. Let's go do things. Who would you rather be on a date with? I'm picking zinc. Now, okay, you may have personal preferences, you may be tired after all these snowy days, you may just want to sit on the couch, but in general terms, the more active thing is more interesting. And this is, of course, we are completely anthropomorphizing chemicals, which we should never do, and you understand that it's a metaphor, right? Yes, okay. Things that are more active replace things that are less active. You will drop the couch potato for the interesting, fun date that wants to go places anytime. Now, let's try a different example. What if we had zinc, ZnCl2, and we put some straight copper metal in it? Based on what we just discussed, is that reaction going to run? No, because there's no way you're going to drop zinc, your fun, exciting, let's go places, let's do things, let's go see people, let's go hear music, let's go do something, for copper. No, let's just sit here. You want to make some popcorn? No. Like, copper's really just not a lot of fun. So the thing that is more active always replaces the thing that is less active. A couple other points to consider when we're looking at this chart. Let me select, copy, paste. Hey, that worked really well. If you look at this chart, there's more information than just the vertical ranking of who's more and less active. Each section has got additional information. So if we take lithium and we throw a chunk of lithium into room temperature water, will it react? Yeah. Everything in this first box reacts with cold water, it reacts with acids, and it can replace hydrogen. So we could take lithium plus water, and based on what we were told, what's the lithium going to replace? It's going to replace hydrogen. So what will our product be? Well, we're going to get hydrogen gas. Anytime you got something replacing the hydrogen in water, we form hydrogen gas. And hydrogen gas, this is one of those little notes to yourself to make. Hydrogen gas is a really common product whenever you have a metal reacting with water or an acid. We generally split off some hydrogen, we get little bubbles. And our other product would be lithium oxide, and that would be Li2. I don't have room to write that. Li2O, lithium oxide. Okay, let's look at our second box. So this is magnesium through cadmium. So if I put a chunk of aluminum in cold water. So let's give you some more information because we know how to use chemical symbols like this. Okay, if I put aluminum in water at 20 degrees Celsius, that's room temperature, you're sitting in about a 20-degree room, will it react? Why not? Because these in this block will react with steam, but not with cold water. So no reaction. No reaction is going to happen. And we very often just will write NR. What if we put aluminum into nitric acid? So look at the additional information you're given there. So, Kaylee, you're saying it will react? Read to me the text that justifies that. And acids replacing hydrogen. So what are our products going to be here? Give me one product. Somebody in the first row. You guys can divvy it up. Metal and an acid, we said one common product is hydrogen gas. Pretty much anytime we have a metal and an acid or a metal reacting with water, we're going to generate hydrogen gas. We're going to get bubbles. Okay, what would our other product be? What's left? Oops. What's our other product? Well, aluminum nitrate, you're right, but that's not the formula for aluminum nitrate, so you have to be real careful. Remember, aluminum is a 3+ ion, nitrate is a 1-, so what's our formula? Yep, AlNO3 3 times. Okay. So you want to try some halogens together, and then I'm going to give you a practice sheet, and I'm going to just turn you loose, and you're going to practice. Tomorrow you will have a FIP that will cover reaction types. Remember those? Like sometime last year we talked about them. Reaction types, activity series, and predicting products. That's Tuesday. Wednesday, homework is now due. Thursday is your test. Okay? All right, let's do a couple halogen examples. So we'll go back here, select, copy. Get another copy of this. Okay. The halogens are much simpler. There are only 4 of them that we do anything with here. So we've got fluoride, chloride, bromide, and iodine in descending order. So fluorine, fluoride ions are the most active of these. So what if we have ammonia? Ammonia halogen compounds are so common. That's why we use them so much. Whoops. NH4I. And we toss in some chlorine. So the first question is just, will this reaction run? Yay or nay? Yay. Yeah, this reaction will definitely run. And so then the next step is predicting our product. So what would our products be? We know chlorine will replace iodine. What's the formula for ammonium chloride? Yep, get out the Bible. Check your charges if you need to. NH4Cl plus I2. Yep, nice. Let's move that over a little bit. Okay. So yeah, and we've got correctly written formulas. Now, of course, we'd have to balance that, and that would do it. So it's key when you're predicting products, make sure you're writing correct formulas, and then make sure that if you're asked for a balanced chemical reaction, you're balancing correctly. So just putting it all together. Okay, let's do one more with halogens, and I'll hand you a practice sheet. So let's do sodium chloride plus bromine. Will this reaction run? Okay. Ella. No. Okay, so we don't have to predict products. We don't have to do anything. All we have to write is no reaction. No reaction occurs. Okay. It's beyond the scope of this course, but some of you who are rather clever critters, which is many of you, can probably also figure out that you can sort of figure whether or not a reaction is going to be reversible based on this. If you've got two things that are very, very different in reactivity, if one really readily replaces something else, you're probably not going to run a reverse reaction, because whatever is now in a compound with that more active thing has no interest in going back to its old couch potato dud of a date. So you can look at reversibility in these terms also. Okay, questions, comments, concerns? I'm going to give you some practice and turn you loose.